Hello everyone, my name is Jason Wong. I am a PhD student in the Computer Engineering Department at the University of Alberta, and I would like to thank ASI for giving us the opportunity to present our research on applying machine learning on 3D ultrasound images to aid Cobb angle measurement of children with scoliosis. Adolescent idiopathic scoliosis, or AIS, is a three-dimensional spinal condition found in adolescents where the spine has lateral curvature and vertebral rotation. And so to give you an idea of what it looks like from a clinical perspective, here is an image of a healthy adolescent, and here is an image of an adolescent with AIS. And you'll notice that there are markings on the rightmost image. Those indicate the Cobb angle, which quantifies the severity of the lateral curvature and is used to both diagnose and monitor the severity of AIS. You'll also notice that these two images were performed on radiographs. That is the standard imaging method to monitor AIS, but recently a few groups have been pushing for ultrasound as an alternative imaging method. And the main reasons for this are that it is radiation-free, it inherently provides 3D information, and it provides similar accuracy and reliability to radiography in terms of measuring the deformity. However, the main drawback is that it is less intuitive and therefore more time-consuming to measure. And this ends up being quite a barrier of entry for clinics to adopt ultrasound in their scoliosis diagnosis, and we really want to try to remedy that. And so that brings me to the objectives of our study, which are to apply machine learning to aid Cobb angle measurement on ultrasonographs, and also to determine the validity of the machine learning aided method. And so the procedure by which we measure these scans is we first process the scans to both improve the quality and center the spine. We then train a machine learning model, in this case a convolutional neural network, to segment these vertebral features called laminae for us. And then using these laminae, we can measure the Cobb angle, which essentially consists of pairing up laminae on the same vertebra, identifying the steepest pairs, and then using those pairs to get our Cobb angles. And so to perform our pilot study, we started by looking through our local scoliosis records for children diagnosed with AIS, had a Cobb angle less than 45 degrees, and had no prior surgery. Using these criteria, 37 scans were randomly selected, among which there were 73 curves, and you can see the population characteristics listed there. We then measured these scans in the same procedure that I outlined in the previous slide, and we compared these measurements with manual ones on the same ultrasonograph performed by raters with more than 3 years of experience. Finally, we calculated the percent within clinical acceptance, in this case within at most 5 degrees of the manual measurements, the mean absolute difference, and the inter-method intraclass correlation coefficient. And so here's a scatter plot of the machine learning aided versus the manual measurements, separated by region, with blue being upper thoracic main thoracic, or the upper half of the spine, and orange being thoracolumbar lumbar, or the lower half of the spine. In the end, 66 out of 73 curves were detected, with 74% of measurements being within clinical acceptance, and a mean absolute difference of 3.7 degrees. The ICC was 0.85, demonstrating great reliability, and the average measurement time when using the model's predicted laminae was 30 seconds, with network predictions taking on average less than 1 second. This did improve upon the average 90 seconds it takes an experienced rater to manually measure. We then further analyzed the results by both region and severity, and pointing out the more informative trends here, you'll notice that the method performed worse on thoracolumbar lumbar curves, and the reason we think this is that the vertebrae in this region have greater bony surface area that can cause the ultrasound signals to scatter, making it harder to identify the centers of laminae. In terms of curve severity, there was no significant difference in performance, but you'll notice that 6 out of 7 of the undetected curves came from the mild curve severity group, although this is expected since the smaller the curve, the harder it is to detect. But in conclusion, the machine learning aided Cobb angle measurement method was feasible, demonstrating great reliability and quicker measurement time. We identified these systematic errors, which is promising since we know which areas to focus on to boost the accuracy. And in terms of future work, we do plan on improving the accuracy through post-processing methods. In this case, we can use other features of the spine to help guide lamina placement, or also improving the model by adding more labeled data for training. Finally, we plan on developing code for full automation to truly make ultrasound a more accessible diagnostic imaging method for AIS, thereby reducing the risk of cancer in these children. And with that, I would like to thank you all for listening, and I will be happy to take your questions in the Q&A session. Thank you.